Hello, everyone. I hope you're all doing well. Welcome to the third and last recording of the exam NSS, where I'll be taking you through questions 7, 8, and 9. So, once again, just remember that there are 9 questions in the entire paper. However, you will be answering just 6 of them. So, section A, your compulsory section, where all 3 questions need to be answered, and then section B, C, and D, has 2 questions each. You will be selecting 1 question per section. So the first one that you see up on the screen is question 7. And remember, just to reiterate, this is a follow up from the previous recording and I'm just going to write it on the right hand side here. Sorry, let me change that to a pen rather than a highlighter. So remember section C, which is the last thing that we were working with, was based on question 7 and question 6. Question 6 we actually did in the previous recording. So question 6 was based on learning unit 5. And then question 7, which we're going to do now, is based on learning unit 6 and 7 combined. So there's actually 2 learning units that are covered in this one question in the exam. And remember, you are selecting from both of these. You are either answering question 6 or you are answering question 7. We've already covered question 6 in the previous recording. And remember, this learning unit itself was also covered in your assignment 2. Learning unit 5 was done in assignment 2. And then learning unit 6 and 7 was not covered in either of your assignments. So if that is the option that you are selecting, please do remember that both of the learning units are covered in question 7 here. So you are selecting between question 6 or question 7. You are not answering both of them. So learning unit 6 is your sampling distributions learning unit 6 is your probability distributions, and learning unit 7 are your sampling distributions. So I'm just going to write that down here just for your own knowledge, so when you are studying, you know which learning units exactly are being tested in each question. And learning unit 7 is a sampling distribution. So the reason they are combined in this question is because learning unit 7, I can't put in the word distribution here, but it is sampling distributions. So as I was saying, the reason that we have 2 learning units in one question here is because learning unit 6 is looking at your binomial and your Poisson distributions. And then towards the end of the learning unit, you find that we sort of start with your sampling distributions and then it's continued into learning unit 7. So it's basically that learning unit 7 is a build up on learning unit 6. So it is separated into 2 separate learning units. However, the content for learning unit 7 does start at the end of learning unit 6. So it's just a continuation, and this is why they've combined the 2 in this specific question. And again, you then have the choice between the question 6 covering learning unit 5 and then question 7, which is learning unit 6 and 7. So let's go ahead and get started with the question. The first question says to you, on average, 6 customers make a purchase from a retail website in any given 30-minute period. Now, before even moving on from this, just right at the very beginning, while we are looking at that first sentence, let's have a look at what keywords we can identify that will help us understand which distribution we are working with. So remember, this is learning unit 6 and learning unit 7 that is covered in this question. And learning unit 6 is made up of, so I'm just going to say here, learning unit 6 and 7. Learning unit 6 is the first part made up of a binomial and a Poisson distribution. And then it also has a normal distribution, which is then continued into learning unit 7. So here, the moment they've mentioned to you the words on average, this immediately says to you that you are working with a Poisson distribution. So I'm going to highlight the words on average here, and I'm also going to write above it that immediately the moment you see the words on average, it immediately says to you it is a Poisson distribution that we're working with. So just from that, we've already identified one key factor in terms of this calculation. So it says on average, there were 6 customers that made a purchase from a retail website in any given 30-minute period. So this average of 6 that they've given to you here, and I'm going to also write down at the top of it, is the average figure which is denoted by the letter A in the formula. So I'm going to indicate that A is equal to 6 in a 30-minute period. That's also very important here to note the time component that they mentioned. So I'm going to highlight that it's a 30-minute period. And what I'm going to do is I'm actually going to write that next to the number 6. I'm going to say that A is equal to 6 if it's a 30-minute period. Now, I'll explain to you as we continue to read why that was so important. So then they said to you in the actual question now, what is the probability that less than 3 customers will make a purchase from the retail website in any given 15-minute period, and then interpret your answer. Now, it's very important to have read that carefully because you are quite easily going to read through that sentence and that question and not realize and pick up on the little things like the fact that for the first part of it, they said to you the average was 6 for a 30-minute period. However, what the question was actually asking you was, what is the probability of there being less than 3 customers, not in a 30-minute period, but rather a 15-minute period? So please do pay attention to these little things because it's quite easy to just read through a question and not really pick up on these things and just assume that, they mentioned to us in the first part that it's a 30-minute period and that probably won't change. But obviously, there's these little things that really do make a difference in your questions and respective calculations. So here, that means we need to adjust the value of A that we had written out at the top. Remember, we said that A is equal to 6 for a 30-minute period. This is now half of that time period. So the A value would also be halved respectively. So that would mean for our question and to answer this question, we actually need to halve the A value as well. So in a 15-minute period now, actually, let me just write down the number itself. In a 15-minute period, this would make A equal to 3. So I'm just going to say in 15 minutes. So now that we know we had to adjust the value of A, and we also know we're working with a Poisson distribution, and we also know that they're looking for the probability of less than 3, we can go ahead and start answering the question. So firstly, the fact that they said what is the probability that less than 3 customers means that it's lower than 3. So we're looking at, and I'm just going to do it on this side, 7.1. We're looking at the probability of x being less than 3. So remember, it's not inclusive of 3, they just said less than 3. So that would mean that it would be every number lower than 3. And that would mean, and I'm just going to write that out here first, and then we'll write it out in the formula. That would be everything lower than 3, which is 2, 1, and 0. So this then means that we're going to say that the probability of x being less than equal to 3 is equal to the probability of x being equal to 2, x being equal to 1. So you're adding them, remember. So it's the probability of x being equal to 2 plus the probability of x being equal to 1 plus the probability of x being equal to 0. You can also just do it in ascending order and say first probability of x being equal to 0 plus the probability of x being equal to 1 plus the probability of x being equal to 2. So you can change that as well. You can put them in normal sequential ascending order. So let's actually just do that. Let's put them in normal ascending order. So 0, 1, and 2. And this is now basically everything that is below the number 3. So we know now that we are working with the values of x being 0, 1, and 2. And we knew that it was a Poisson distribution. So immediately we can write down the formula now of your Poisson distribution. So for Poisson distribution, and I'm just going to write down the formula on the left-hand side here, and then we'll actually apply it in the formula on the right. So this is for Poisson distribution, e to the power of minus a multiplied by a to the power of x over x factorial. So we're just going to apply this formula 3 times, each time just changing the value of x in the formula so that we can replace it with the 0, get the answer for 1, get the answer for 2, and then just add them up. So it's quite nice because the way in which this formula is structured, you can actually just put in the formula into one long answer here and just literally substitute the value for x each time. So the first time around, x is equal to 0. I'm just going to put an arrow there to show you which one we're working with. So this would be the first one here where x is equal to 0. And now you're going to say e, remember e stays as is, so I'm actually just going to write down e for all of them. Then it's to the power of minus a, and remember this time for our answer a is equal to 3, so it's to the power of minus 3 minus 3 minus 3, and then it's multiplied by, remember the dot indicates multiplication, and I'm actually just going to put in the multiplication sign instead of just putting in the dot. Then it says a again, so let's write down a again. And now this is where it's going to differ for each one. So it says to the power of x and then over x factorial. So the first time around, x is equal to 0. So it'll be to the power of 0 over 0 factorial. The next one is 1. So it'll be to the power of 1 over 1 factorial. And then it's 2. So it'll be to the power of 2 over 2 factorial. And you're done. That's it for your formula. And now you can put that whole bit into your calculators. So remember, on your calculators, you will literally put in the symbol E. It does appear on your calculator. It is a symbol. It's above the ln sign on your calculator in the right-hand corner. So you have your on button. Below the on button is the log button, and below that is ln. And you'll see that it's above the ln button. So you'll have to press shift and then the ln button, and this would give you the function of E. So you'll put in the respective values. On your calculator, you can actually put in this whole thing, and it will allow you to calculate your answer. So once you put that into your calculator, it will give you an answer of 0.4232. Please always leave this as 4 decimals. And then in your interpretation, you will convert it to a percentage to 2 decimal places. So here, your interpretation, you can literally just look at the question and use this to interpret. So literally take what the question was asking you and just convert it so that it reads as a closing statement. And remember, this was looking at the probability that less than 3 customers will make a purchase from the retail website in that 15-minute period. So you will now say that therefore there is a 42.32% probability that less than 3 customers will make a purchase from the retail website. And that is it. Okay, So that is your question 7.1. It's your Poisson distribution. Let's look at 7.2. So 7.2 says Wildcat Tire and Wheels Pty claim that the time taken by its employees to change a tire on an SUV is normally distributed with an average time, which is represented by the symbol mu, of 10.5 minutes and a standard deviation of 2.35 minutes. So immediately from this, always when it comes to it being a normal distribution, they have given you the population average of 10.5 and they've given you the population standard deviation here, which again you can see from the symbol is 2.35. Then they said, what is the probability that a randomly selected employee will take less than 10.85 minutes to change a tire on an SUV, and interpret your answer? So this question is based on your normal distribution or your sampling distributions. So here we have identified from the words normally distributed that it is a normal distribution. And also the fact that they gave you the population average of 10.5. And in this case, they gave you the population standard deviation of 2.35. This indicates to you that it is again a normal distribution or a sampling distribution question, and you are using a Z critical limit here or a Z value in your question. So let's go ahead and look at how to answer this. So I'm just going to erase whatever is on the screen at the moment because we need a bit of space for this. Okay, so now that we know what type of question we're working with, let's get started. So with a normal distribution, and I've mentioned this to my class personally. I'm not sure if Daryl has done the same with his class, but generally I say to my students, draw up the bell-shaped curve and use that as an indication to tell you what rule needs to be applied. Because even though there are no marks that are actually allocated to this bell-shaped curve, it really proves to be so useful when you look at it, put on figures onto that diagram, and then visualize what's actually going on. It helps you quite easily to identify the diagram. So if you have used this method, please continue to do so. It really will not set you on the wrong path. It really makes it quite easy. But if you haven't, if Daryl has taught you a different way, then please do follow his way. There is no wrong way of doing it. It's just that I prefer with my classes to teach them the method of drawing up the diagram, visualizing, plotting figures, visualizing in which direction we're moving, and then respectively apply the rule. So please here, just remember that if you were not taught this way, there is no hard and fast rule in terms of it. If you were not taught to draw up the diagram, please don't stress about that. You don't need to learn it. You don't have to have the diagram, but it's just a method that I use to teach. Okay, so back to the question. As I was saying, the way in which I like to teach this is to firstly draw up the bell-shaped curve, which looks like this. And down the center, we plot the population value that was given to us. And the population value that was given to us was the 10.5 average. So we're going to plot in the 10.5. And now we look at the actual question itself. So the question itself said, what is the probability that a randomly selected employee will take less than 10.85? So the first thing we're going to do is plot down the 10.85, which would just fall somewhere to the right. Remember, this is a normal number line, so it increases to the right and it decreases to the left. And then remember, they said less than 10.85. So now we're going to say less than 10.85 would be in this direction. And if you're moving towards the central line and away from it, past that central line, this indicates to you that the rule is 0.5 plus. And that's it in terms of drawing up the diagram. And you now have identified that this is the rule that we are going to apply at the end of this question. So this then makes it so much easier to just look at the diagram. We know in which direction we're moving, and we've now been able to identify what the respective rule is. Now you can go on to calculate the value of z. So z, remember, when it comes to a mean, is calculated as x bar minus mu over the standard deviation over the root of n. So with this, you're going to remember, look at what was given to you, and everything here was given to you. You have x bar, that's the 10.85 that they gave to you in the question itself. So this here is x bar. Sorry, I'm just going to erase the red parts that I had underlined here or circled. And we're going to highlight. So x bar is the 10.85. The mu value, they respectively did tell you that in the information. And then the standard deviation, they did say to you here. And your n value, they did not tell you what n was in so many words, but they did say to you in the question, what is the probability that a randomly selected employee, so the word a says to you that n is basically equal to 1. It's one person that they're looking at, and what the probability is of that person taking less than 10.85 minutes to change a tire. So that means that n is equal to 1 in your calculation, and you actually don't even have to put that into the formula. Whenever n is equal to 1, you basically will just disregard this denominator here. So you actually are just saying, and I'm actually going to remove it, you're actually just saying that the denominator is the standard deviation. But if you want to put in over the root of 1 as n is equal to 1, that's perfectly fine as well. I mean, it's not going to alter your answer in any way, but it's just that it's not necessary to put it in when you have n equal to 1. So let's now put in the values that we need for this formula. So it's x bar, which is 10.85 minus mu, which is 10.5, over your standard deviation, which is 2.35. And as I said, you don't need to put in over the root of n, but if you want to, you can. But basically, the root of 1 is 1. So you don't actually need that for your denominator. So when you put that into your calculators, this would give you 0.15. And now all you're going to do once you have this is go to your tables. Now I'm going to, and this is because you want the value of P, you want your probability. So I'm going to actually just tell you what the value of P is. It is actually in the slides. I've actually put it into this document. But the only problem I'm having is if I skip to it, it's not going to, it's actually going to stop this recording. So I'm not going to skip to it, but I'm just going to tell you how to read off your table. I'm sure your lecturer has discussed it with you. Daryl would have discussed it with his class. I've discussed it with my class. But I'm just going to reiterate in terms of how to read off the tables. Remember, this is table 1 of the appendix. And all you're going to do is, on table 1, you'll find that it's a whole huge table that has a whole lot of values, Z values, and you're going to read off a probability from this table. So basically, you're going to look for the first 2 digits going across, coming down the first column. So 0.1 would be somewhere right at the top because 0.0 is generally the first one. So 0.1 would be somewhere here. And then the last digit, remember, it's read across and there's always a 0.0 before it. So you literally just take the last digit now because you've already identified the first 2 here. The 0.1 coming down the first column. Now you just need the 5. So you're going to locate going across. Remember, there's always a 0.0 ahead of it, and then you put in the 5. So you look for 0.05 going across, and this would then be a respective p-value. It should be somewhere around here. So if you go in line with 0.01 and 0.1 and 0.05, the respective value here is 0.0596. And that would be the value of P, your probability from this table. So please make sure to remember the first two digits, the whatever the first number is, and then after the comma, the next number. So the first two digits are read down the first column, and the last number, there's always a zero point 0.0 ahead of it, and it's read going across. So if it was one, if this was one, let's just change this. Sorry, I just want to show it to you here. Let's just say, and I'm just giving you an example here. If this was 1.28, for instance, the 1.2, you'd locate going down the first column. So somewhere here, for example. And then the 8, there's always a 0.0 ahead of it. So it'll be 0.08. And that would be somewhere here towards the end. So in line with 1.2 and 0.08, you'd locate your value like that. All right, so I'm just going to remove this. And just remember the 0.0596, and I'm going to write that down here. Okay, so just 0.15, remember that was, and this is 0.0596. Now, once we have the 0.0596, all you're going to do is go back to that rule that we identified at the top, and you're going to say now, therefore, oops, sorry, I'm working with my highlighter. All you're going to do now is say that therefore this means 0.5 plus this answer of 0.0596 is equal to 0.5596, and that's your final answer, which you will now make a percentage in your interpretation. So in your interpretation, again, just look at the question and convert it so that it reads as a closing statement. So you're going to say, therefore, the probability, or you can say there is a 55.96% probability that a randomly selected employee will take less than 10.85 minutes to change a tire on an SUV. It's quite a mouthful, but you literally then just need to look at your question. The last part of the entire paragraph is usually your question. So all you have to do then is take the last part, the question itself, manipulate it and change it so that it will read as a closing statement. All right, so that's question 7.2. Let's look at question 7.3. So 7.3 says, it has been found that the age at which South Africans pass a driving test is normally distributed with a mean of, and again here they've given you the, oops, sorry about that. So they've given you the mean of 21.75 and a standard deviation of 1.35 years. If we randomly select a sample of 115 South Africans, the first question, 7.3.1, said determine the standard error for the sample. So the standard error is actually the denominator of the formula at the top here that I wrote down for Z. This is the standard error. It's the standard deviation over the root of n. So let's calculate that, and let me just remove whatever we were working with here. Okay, so here, and before I move on as well, what I'm actually going to do is just write out what we have so far. You have mu, that's 21.75. We have the standard deviation, it's 1.35. We have n now. They did tell us it was a sample of 115. And so far, that's all we have. So for question 3.1, as I said, it is the formula. The formula is denominator. So the Z value formula denominator. So I'm just going to write down the Z formula again here. It's x bar minus mu over your standard deviation over the root of n. So it's just the denominator, which is the standard deviation, over the root of n. The standard deviation is 1.35. The n value is 115, so it's over the root of 115, and that is 0.13. And that's question 7.3.1 done. Now for question 7.3.2. It says, what is the probability that for the sample, the average age at which the participants pass their driving test will lie between, so there's two values here, 21.95 years and 22.15 years, and interpret your answer. So first things first here, you have two values that you're working with. So this means that there are two Z values. Also, we still follow the same process that we did earlier. We draw up the diagram, we plot down the population value down the center, we then plot down the sample values, and we determine what rule is being applied. The other thing that we need to make note of, and this is very, very important, is that we had been given the sample size of 115. So we need to remember that there is an n value in the formula. It's not like the previous one that we were working with. Here there is an n value. All right, so let's get started with this then. So I'm going to draw up the diagram at the top. Sorry, again, I forgot to change it to the pen. So here's a bell-shaped curve. Remember, you can just draw this up roughly. In fact, you don't even have to put it into the question paper. Sorry, your answer booklet. You can just write it on the question paper if you want. Just to assess what rule is being applied so that it makes it easier when you get to the final step to now apply the rule. So you draw up your bell-shaped curve. Down the center, you plot your population value, which is the 21.75. And now we plot the sample values, which literally was what the question asked for. So it's 21.95, which would fall somewhere on the right here, 21.95, for example. And then 22.15, which is even further somewhere here. So now we know where the sample values lie. And when we are saying between 21.95 and the 22.15, we're talking about this space, the part that I've indicated with the curly bracket. Now, whenever you find that there are two values and both of them fall on one side of the straight line down the center, so they both fall on one side of the central line, this means the rule is subtraction. So again, this is something that your lecturer would have discussed with you. And the rules are when they fall on one side, even if it was both on the left-hand side, as long as they're on one side of the central line, it means the rule that will be applied is the subtraction rule. So let's continue now that we know the rule. We have two separate Z values. So I'm going to just draw a line down the center here so that we can calculate the Z values. And that would mean we also have two probabilities. So let's now put in the values for Z and calculate that so we can then get to our respective probabilities and then subtract, work out the difference between them. So here x bar, the first x bar value is the 21.95. The second x bar value is the 22.15. So this is 21.95 and this is 22.15. Then you're going to say minus, sorry about that, it just removed everything. So this again is 22.15 minus, and then 21.95 minus. Mu is your 21.75. We wrote that down already. So minus 21.75. And here as well, minus 21.75. Then it's over your standard deviation, which is 1.35. So 1.35 on both sides. And then it's over the root of n. So over the root of n is 115. Okay, so 115 as your denominator of the denominator. And then you put this onto your calculators, and this would give you 1.59 for the first one. And the second one would give you 3.18. All right, so once again, you'll go to table 1 of your appendix. Remember, the first two digits are read coming down the first column. So for example, 1.59, you'll look for in the first column here. And then going across, you'll look for, it'll always be 0.0 and then the last digit. So the 9 will come in here. In line with 0.09 and 1.5, your respective value here is 0.4441. So I'm just going to erase whatever's here, and we'll work with just the value. So I'm just going to write down the value itself. So this is 0.4441. Then for the next one, 3.18, again, 3.1, you'll come and look for you'll look for that in your first column, 3.1, and then coming down that first column, and then the 8, it will be 0.08, would be somewhere towards the end. It's a second last column generally. And then in line with the 3.1 and the 0.08, your respective value in the table is then 0.49926. So I'm just going to remove that. So remember, come down the first column for the first two digits and then go across for the last one. So this is 0.49926. All right, so now that we have the respective p-values, all we have to do here is now just work out the difference between them. Remember, that's because we identified at the very beginning that it is a subtraction rule, and we need to now apply that. So it's always the higher of the two numbers minus the lower. And this is because probabilities can never be negative. So we can't take the smaller number or the first number and then subtract the second one, because that would give us a negative value. And again, probabilities can never be negative. They are non-negative in nature or just positive in nature. So you'd look for the higher of the two, which is the 0.49926, and then you would say that minus the smaller number, which is the 0.4441. So this is 0.05516. That's your final answer, but now you need to interpret. So you will say there is a 5 point, let's leave it as 2 decimal places. So we'll make it 5.52%. So there's a 5.52% probability that the average age, this is what they were looking at here, the average age at which the participants pass their driving test will lie between 21.95 and 22.15 years. And that is your answer. All right, so this is question 7 done and dusted. Let us move on to section D. So remember, this was section C still. We looked at question 6 in the previous recording. This was question 7. You have the choice between the two, and that was your second section where you had choices. Now for the last section, let's move on to section D. So section D has two questions once again. You have question 8 and question 9. You are going to select from these two. You are not going to answer both of them. So as per the instructions at the top, section D, you will answer only one question. Choose either question 8 or question 9, but not both of them. So in question 8, we are looking at learning unit 8. So learning unit 8 is your hypothesis testing. So I'm just going to write down this next to it as well. Hypothesis testing. And remember, hypothesis testing is where we saw that there were 5 steps that needs to be followed at all times when answering these type of questions. And also we need to understand that with hypothesis testing, there can be a two-tail test, there can be a one-sided upper tail test, or a one-sided lower tail test. So let's go ahead and look at the questions here. Question 8.1 says a small construction company claims that 23% of its clients are based in Nelspruit. So what's important to note from this question is two things. Firstly, just from that opening statement, the first and most obvious thing that we can identify is that we're working with proportions. The reason we say this is because they have given you a percentage in that question, so, or in that statement. So we are not working with a mean or an average because they didn't say anything about the average dot dot dot. They said that it is a 23% of their clients that are based in Nelspruit. So immediately here, we know we're working with a proportion. The second thing we can also gauge from this first sentence is that we are working with a two-tailed test. And how we could identify that is the fact that they claim that it's 23% of its clients, meaning they are referring to exactly 23%. It's not more than 23%, it's not less than 23%, it's exactly 23%. So the fact that they didn't use any of those other words like less than, more than, at least, at most, and so on, they just said 23% means that it is a two-tail test. So I'm actually going to write that out as well, just to show you that we know what we're working with immediately from that sentence. Let me just erase here at the top and I'll write that down. So immediately from just that. Sorry about that. I think I got cut off there for a second. As I was saying, and I'll just repeat what I had said here, that we know that we're working with a two-tailed test, and we also know that we're working with a proportion because they gave us a percentage, and that 23% itself is actually the population proportion, which is denoted by the symbol pi. And pi then is 23%, or as a decimal, that's 0.23. Then it says, and we can read the rest of the question now, that they want us to test this claim at the 1% significance level. So that's quite important as well. 1% significance level. If a survey found that out of 106, out of 700 clients, 168 of them were based in Nelspruit. Now, this 168 out of 700 people is our value of P, which is now the sample proportion. So we know the population proportion from the opening sentence, that was the 0.23. And now we know the sample proportion, which is 168 over 700, which as a decimal is 0.24. So we actually have pretty much everything we need because we know the population proportion, we know the sample proportion, we know the significance level, which is 1%, and we also know that the sample size, which they did say to us, is 700. So we have identified everything necessary for the calculation. Now we can start with it, which is step one, to write out your null and alternate hypotheses. So the null hypothesis, remember, when it's a two-tailed test, will always say equal to, and your alternate hypothesis will always say not equal to. Remember, they must say the opposite to each other, and the null must always have the equality sign. So since we're working with a proportion, we must say pi in the null and alternate hypotheses, and you must put in the population value. So that's the 23. So your null will say that pi is equal to 23 or 0.23. It is preferable that you work with it as a decimal here. So it'll be pi is equal to 0.23 in the null hypothesis, and the alternate hypothesis will say that the pi value is not equal to 0.23. And again here, it would be beneficial for you to write down that this is a two-tailed test because there are marks generally allocated to this. So you've written down that it's a two-tailed test and you've written out your hypotheses as well. Now for the second step, which is to write out your null and alternate, which is to state your acceptance and rejection regions. So generally you just need to state one of them, which is your region of rejection, but you can show both if you'd like. There is no hard and fast rule here, but at the very least your rejection region has to be included. So once again here, just as per my own teaching methods, I do like to draw up a diagram to also just help students visualize when they are identifying their acceptance and rejection region, and also later on when they're concluding where your limits lie, where your values lie, and it just helps you to be able to look at it and say that this is in the acceptance region or this is in the rejection region. So again, if your lecturer has not taught it to you in this way, please don't be stressed out about it or think that you now have to learn this method. This is just my own teaching method, and you can just follow whatever you are comfortable with. Okay, so I like to, in step 2 now, draw up your bell-shaped curve again, and we know it's a two-tailed test, so we know that we have two critical limits on either side of that bell-shaped curve, and we know that both critical limits and everything within it is your region of acceptance, and anything greater than on the right hand side or less than on the left hand side is your region of rejection. Now, how do we know what those critical limits are? What are the actual values of those critical limits? Now, this again is requiring a table. You're either working with the tables from the end of your formula sheet, or you have to remember the figures, which I will show you at the end. I'll just show you the tables at the end, but as I said, I can't actually skip to it now, because if I'm skipping to it now, then I'm going to not be able to come back and continue recording on this page. So unfortunately, I won't be able to skip to it now, but you know which tables you're working with. You either have your Z limit or you have a T limit. So in this case, because you have a two-tailed test and you are working with a proportion, and also you know your significance level, you are working with the table that is in the Learning Unit 8 content, in your slides, in your textbook, in the actual chapter itself, not the statistical tables at the end of the textbook or at the end of your formula sheet. So you're not working with those statistical tables, you are working with the one that is in the actual learning unit itself, in your slides, or in the respective chapter in the textbook. So we need to know what type of test we have, which we already know from the top is a two-tailed test. And then we also need to know what your significance level is, which we were able to identify from the information is a 1% significance level. So all you need to do now is go to that table. It's a table that looks like this. I'm just going to roughly draw it up. And then it has your different critical it has your different significance levels here. For example, 1.1%, 5%, 10%, then again 1, 5, and 10, then again 1, 5, and 10. Then you have the type of test in the next column. I'm just showing you just to remind you what the table looks like. And then, for example, they have here at the top, I think it's the one-sided ones first. They'll have one-sided and upper-tailed will be these three. Then these three will be maybe the one-sided lower-tailed. I can't remember if it's exactly in the same order. I don't think so though. I think the two-tailed one is the first one. I can't really remember right now. Okay, so they have separated it, and then all you have to do is, for instance, we know that we're working with a two-tailed test from the top. So you'll know that these are the ones we're working with. And we know that it's a 1% significance level. So you'll go to 1%. And in line with that, it will give you the Z limits in the last column. So the Z limits for a 1% two-tailed test are plus minus 2.58. So what that actually means now, and I'm just going to erase this because we don't need it. So this then tells us that, sorry, I'm actually going to just erase this here so we don't get distracted with all of this writing and circling. Okay, so as I was saying, we know then that it's a 1% and it's a two-tailed test. So it was plus minus 2.58. That means on the right-hand side, it's a positive or the plus 2.58. And on the left-hand side, it's a negative 2.58. So now that we've been able to visualize this, we can now write that out in words because this is where the marks are actually allocated. So you need to firstly say that we use a Z critical limit of plus minus 2.58 and then just write it out in words. And as I said, you actually only need to write down the rejection region, but you can write down everything if you want. You can write down the acceptance and the rejection region, but I'm just going to write down the rejection region here. So you're going to say then that you will reject the null hypothesis if the Z value is either on the right hand side greater than 2.58 or on the left hand side if Z is less than minus 2.58. And that's actually it for step 2. That's your region of acceptance and rejection. Now we need to move on to calculating the Z value itself. So to calculate the Z value, we're using the Z value formula that you would have also used in Learning Unit 7. And that would have been for a proportion. I'm actually not going to write it here. I'm going to write it down in rough here. So Z is equal to, at the top, P minus pi over the square root of pi multiplied by 1 minus pi over n. So here now, I'm going to plug in the actual values. So we know that P is the 0.24 that we calculated here. Please remember that you do need to show the working out of P, and there's a mark allocated to that. So it's 0.24 minus, then it's minus pi, which we wrote down here There was a mark allocated to this in the formula. Also, it needs to be converted to a decimal, so 0.23, and then it's over pi. Actually, first it's a square root of pi in the numerator multiplied by 1 minus pi over n, and n is the 700. So this then gives us a value of 0.63. And what we're going to now do, well, that's step 3 done. You've calculated your test statistic. What we're now going to do for step 4 and 5, which is usually done together, we're going to look at where does a 0.63 fall on your diagram. And this is why the diagram is so useful, because now you can actually plot the 0.63, and the 0.63 will naturally fall somewhere towards the center because it is obviously below the 2.58. So this is now in your region of acceptance. And like that, you can see that we've now literally been able to visualize and identify that this was the acceptance region. So the diagram is really useful in that sense. We now know it's the acceptance region, so we now can conclude. So now you're going to say, and remember, we generally try and say we do not reject. Instead of just outright saying accept because it's the acceptance region, we try and stick to using the words do not reject. So you'll say in your conclusion now, therefore, do not reject the null hypothesis. And now we need to say, what does this mean? So remember, the claim that they were making in the question was that 23% of their clients are based in Nelspruit. So basically, if you go back to the null here, the claim was that it is exactly 23%. So if we're saying we accept this null, if we are saying do not reject it, that means that the null hypothesis is probably true. So you will say then, we do not reject the null hypothesis because, or we can conclude that the claim that they're making is probably true. And that's it. That's literally all you need to say in terms of your conclusion or your interpretation. You just need to say, am I rejecting or am I not rejecting? Meaning I'm accepting if I'm not rejecting. So in this case, we were accepting, but we just say we do not reject. And then what does that mean? If we're saying we don't reject the null, what do we actually mean? Is their claim true? Is it not true? What does it actually mean? So you're going to say then that we do not reject the null hypothesis and the claim is probably true. So that's question 1 done. Let's look at question 2. So I'm just going to try and do question 2 on the side here. Let's separate it here. Okay, so question 8.2 says, the national manager of a chain of clothes stores claims that on average, now firstly, the word average has been given here, which immediately says to you, you are working with a mean, not a proportion. So you know that you're working with a mean, and then it says the claim is that on average, the store sells 205 Panama hats per month. So now what we can also identify here is that the claim is that they're selling 205 hats per month. They're saying exactly 205. So it's not less than, more than, at least, at most, greater than, and so on. They're just saying 205. So this says to us again immediately that this is a two-tailed test, because it is looking at exactly one number, not more than it, not less than it, nothing of the sort. So this then is also your population value. So this is mu, which is a symbol for a population mean. Then it says, test this claim at the 5% significance level. So I'm going to highlight that. If it was found that over a random sample of 23 months, Now, immediately, this sample size is 23. And remember, whenever we have a small sample size, this indicates to us that we're working with a T limit, not a Z limit. So N is 23, but this also tells us that we're working with a T limit instead of a Z limit. Like here for the previous question, and I'll just highlight so you can see that. Remember, we wrote down on the side here that we have a Z limit. Instead of having a Z limit now, we're working with a T limit. So I'm just going to say here that we will have a T limit. Then they say to you, and I'm just going to backtrack here a bit. It says test his claim at the 5% significance level if it was found that over a random sample of 23 months, the store sold an average of 217 Panama hats per month with a standard deviation of 33 hats per month. So immediately here, the value of 217 is your X bar. It's your sample mean, and your standard deviation is 33. So now we have all of the information that is necessary to calculate or carry out this test. We know that we're working with a mean. We know that we're working with a two-tailed test. We know that we're working with a T limit instead of a Z limit. Now, the test in general is exactly the same idea as question 8.1. We first write out our null and alternate hypotheses, and then we continue with determining the region of acceptance and rejection, calculating the test statistic, concluding or basically identifying are we falling into the region of acceptance and rejection, and then concluding. So here the null and alternate hypotheses, we know that it's a two-tailed test, so we know it will say equal to and not equal to in the null and the alternate. Then we know we're working with a mean, so it will say mu is equal to and not equal to. It's always the population symbol that goes in here. And then we take the mu value itself, which was 205. So mu is equal to 205 in the null, and it's not equal to 205 in the alternate. And then just write down that it is a two-tailed test because, again, there's a mark allocated here. And now we can move on to step 2. So step 2, remember, is your region of acceptance and rejection. It's a two-tailed test, so everything including the critical limit and within it is your region of acceptance. Everything greater than on the right and less than on the left is your region of rejection. Now, how do we determine what the critical limits itself are? Because we're working with a T limit, we need two things. We need your level of significance, which they said to us was 5%. So I'm just going to write down here, A is equal to 5%, which as a decimal is 0.5. Remember, A is your level of significance. It represents your level of significance. So your level of significance is equal to 0.05. And the other thing we need is your degrees of freedom. Because we're working with a T limit, we need A and we need the degrees of freedom. So the degrees of freedom is calculated as N minus 1. And N, as we know, is 23. So minus 1, that gives you 22. And now you're going to go to table 2 of your appendix. So basically at the end of your textbook, or alternatively at the back of your formula sheet, the last thing after your formula sheet. Sometimes they might put it before your formula sheet, but generally it's after it. It would be table 2, your T table. And all you're going to do for the T table is, and I'm just going to remove this so I have some space to show you here. All you're going to do for the T table is the same thing we did in the previous section for the previous question, or the previous question 7. You're going to simply look at the table and you're going to find, I'm just drawing up a rough version here, you're going to find your A value going across, and your degrees of freedom coming down the first column. So your degrees of freedom is 22. You're going to go all the way down to 22, and your A value is 0.05. So you're going to locate 0.05 going across. In line with the 22 and the 0.05, you're going to find your critical limit. So the value here is 2.074. And this, remember, is going to be, because it's two critical limits, there's a positive 2.074 on the right-hand side of the diagram and a negative 2.074 on the left-hand side. So this is now how you get to your T limit, respectively. And I'm just going to erase this table again. And now all we're going to do is just write this out in words. So to write it out in words, again, you only need to write down the rejection region. So you're going to say reject the null hypothesis if the Z, actually now we're working with a T value. So if T is greater than 2.074, or if T is less than minus 2.7, sorry, not 7, 0.74. Okay, so that's your region of acceptance and rejection done and dusted. Now we move on to calculating your Z value. So I'm going to write it on this side. Again, this is exactly the same formula from Learning Unit 7. Remember, the Z value for a mean is x bar minus mu over the standard deviation over the root of n. In this case, our standard deviation, because we're working with the t value, it's s instead of that symbol. So here, let's work with the Z value and plug in what we have. X bar, we know, is 217 minus mu is 205. Let's actually just remove this because we don't need the rest of it. Then it's over. Your standard deviation is 33 over the root of n, which is 23. So this gives you a value of 1.74. And 1.74 then is going to fall somewhere inside that, basically within the boundaries of your acceptance region. So this means that you are accepting, or rather we say we do not reject, your null hypothesis. So now we can conclude, and we're going to say therefore do not reject the null hypothesis. And what does this mean? Now again, where was our claim? They said that they claim that the store does sell 205 hats per month. So their claim was actually in the null hypothesis, that it's equal to 205 hats. So here you're going to say is probably true. We do say probable because we can never guarantee that it will be true. It is just an estimate, but we can say that it is probably true. Sorry, I actually said probable instead of probably. So you're going to say that the claim is probably true. All right, and that is it for question 8. So that's your hypothesis testing. Let's move on to question 9. So question 9 is based on your chi-squared distributions. And this is literally learning unit 9 as well. So I'm just going to write that here, and I'm going to say in brackets that this is the chi-squared test or chi-squared distribution. Okay, so this is where we're following the same 5 steps that we did with hypothesis testing. However, we are only ever looking at a positive upper tail test, meaning it can never be negative, it can never be a lower tail test, and it can never be a two-tail test. So that's the only difference. And then also the way in which we calculate the test statistic does differ. And also, the way in which we write out the null and alternate hypotheses is just using words. We don't need to use symbols like we did with hypothesis testing. So remember, this is again a choice. You are either doing Learning Unit 8, the hypothesis testing question, which was question 8, or this one, question 9, which is based on your chi-squared distribution. So, question 1 says, we wish to determine whether there is a relationship between gender and the preferred brand of cold drink. So, the moment you see the word relationship, or maybe they'd say association, or maybe they'd say they want to test for independence. Immediately, this says to you that it is a test of independence of association or just a test of statistical association. You just want to know, is there a relationship between these two variables? So then they said to you that they surveyed 400 South Africans and these were the results. So in the table that you see here, which is your normal two-way contingency table, they've given you the outcomes of that survey. And this is saying to you that there are three preferred brands of cold drink: Pepsi, Fanta, and Coke. And then they separated them according to gender, male and female, and this was the outcome. Then they said to you, perform an appropriate test at a 5% significance level to determine whether there is a relationship between gender and the preferred brand of cold drink. So immediately here, you know what you're looking for. You're looking for a test of independence or whether there is a relationship between these two variables. So the first step is also to write out your null and alternate hypotheses like we did with Learning Unit 8 or question 8 that we just looked at. So the null and alternate hypotheses will be written out in words here. And the null hypothesis, whenever you're testing for a relationship, it must always say that there is no relationship or that there is no statistical association, or you can also say that there is independence between the variables, meaning there's no dependency or no relationship between them. So in this case, because they were just looking at a relationship, we can just use the words relationship. So your null must always say that there is no relationship, and that will never change. As long as you're testing for a relationship, it will say that there's no relationship in your null hypothesis. So you will say there is no relationship between gender and the preferred brand of cold drink. And your alternate must always say the opposite. So you will say that there is a relationship. I'm just going to put in dittos here, but obviously you'll need to write down that whole sentence. So you'll say there is a relationship between gender and the preferred brand of cold drink. And that's step 1 done. Now for step 2, which is to determine your region of acceptance and rejection. It is always ever a one-sided upper tail test, meaning there is only one critical limit on the right-hand side. Everything including that limit and less than it is your region of acceptance, and everything greater than it is your region of rejection. So now how do we get to that critical limit? So here again, we are using your statistical tables. This is table 3 of your appendix or at the end of your formula sheet. We need two things. We need your level of significance and we need the degrees of freedom. Now, your level of significance, if given to you, you need to convert that to a decimal. That would be 5% as a decimal, which is 0.05. And your degrees of freedom, whenever you have a two-way contingency table given, like here, they gave you a two-way contingency table. It is always calculated as the number of rows minus 1 multiplied by the number of columns minus 1. So the number of rows, when they talk about rows and columns here, they mean only the rows and columns that actually have the categories of information. So for example, there are two rows with categories of information. They are male and female. So that would be two rows. So it would be 2 minus 1, which is 1, multiplied by the columns that have the categories are Pepsi, Fanta, and Coke. So that is 3 columns. So this would be 3 minus 1. So it's 2 minus 1, which is 1, multiplied by 3 minus 1, which is 2. So that gives us a degree of freedom of 2. So again, here you're going to now go to table 3 of your appendix. So here's what the table will look like. A is read going across, so you're going to look for 0.05. The degrees of freedom is read coming down, so you're going to look for 2 in line with 2 and the 0.05. Your critical limit is 5.991. And now that you have your critical limit, you're going to put that onto your diagram. So this is 5.991. And all you need to do now is write out this critical limit. So, write out the rejection region in words. So basically here, all you're doing is saying that you will reject the null hypothesis if the chi-squared statistic is greater than 5.991. So here, sorry, I forgot the word statistic. So chi-squared stat is greater than 5.991. Remember, this is your rejection region where it is greater than that critical limit. So now we are done with step 2. We can move on to step 3, which is to calculate your test statistic. Now to calculate your test statistic, it is a little bit work that needs to be done here. You're going to draw up your table. And please do learn what the headings of these tables need to be. So here you're going to have your respective category. Here you're going to have your observed frequency, your expected frequency, and in the last column, observed minus expected squared over the expected frequency. Okay, so your categories, you can start with the first one. Remember, you always start with the first row and go across, work your way across. And then once you're done with that, you go to the next row and work your way across. So here you're starting with female. And under females, you have Pepsi, which is 54. Then you have Fanta, which is 62. And you have Coke, which is 74. Then you have the males. You're done with the females. So you'll go again across. Pepsi is 56. Fanta, 75. And Coke, 79. All right, so we're done with the FO values. Those are always the ones that are presented to you in the table. So remember, you are always given FO and you are then calculating FE. All right, so FE now is, remember, whenever you have a two-way contingency table, you go to the respective FO in the table. So for example, the first FO value is 54 here. You literally go to 54 in the table and you look at, in line with 54, its row total multiplied by its column total, and then you divide that by the sample size, which is then the last value in the corner. So basically here for this one, you're saying 190 multiplied by 110 over the 400. So this then would give you, and sorry, I'm just going to remove here so we can work with the next one. This would give you 52.25. We generally leave these as 2 decimal places. Now for the next one. In the table here, it's 62. So go to the 62 in the original table. Its row total is 190. Its column total is 137. So 190 multiplied by 137 and then divided by your sample size of 400. And that would give you 65.08. Then the next one is 74. So go to the 74 in the table. So here 74, row total is 190, multiplied by column total is 153. So 190 multiplied by 153 divided by the total of 400. And that would give you 72.68. Now you're done with that. So let's move on to the next one. So the next one is 56 here. So go to 56 in the table here for the males. Again, row total, 210 multiplied by column total, which is 110. And then divide that by the sample size, which is 400. So 210 times 110 over 400, and that would be 57.75. Then the next one is 75. So here's 75 on the table. 210 times 137 divided by 400. And that would be 71.93. And then the last one is 210 multiplied by 153 divided by 400, and that is 80.33. All right, so now in the last column, all we're going to do is literally follow what that heading says. It says, take the value of FO minus the value of FE, square it, and then it's over FE. So for example, and I'm just going to write out the first one here, you're going to say FO is 54 minus FE, its respective FE is 52.25. And then square that over the FE, which is the 52.25. All right, so this is how you'd calculate that. Sorry, I'm just going to take out the working out in the circles. All right, so this is 0.06. Again, please leave these as two decimals. Then the next one is, for example, 62 minus 65.08 squared over 65.08. And then this would give you 0.15. Then the next one is 74 minus 72.68 squared over 72.68. And that's 0.02. And then you'll continue like that. So 56 minus 57.75 squared over 57.75, and that is 0.05. The next is 0.13, and then the last is 0.02. So now you'd add up everything in that last column, and this will give you your chi-squared statistic. And your value here for your chi-squared statistic is 0.43. So once you're done with this, we now need to look at where does the 0.43 fall on the diagram. So on the diagram that we had drawn up here, and once again, you do not have to draw up this diagram. It is not for marks. The marks are actually just for this that I wrote down on the side here. But again, it is so useful to have it, even if it's just in your question paper, just so that you can visualize and see where your values lie. So here it is in the region of acceptance. So now you're going to say, therefore, we do not reject the null hypothesis. And now again, we need to say, what does that mean? So you'll say, which indicates that. And now go back to your null and alternate hypotheses. If we're saying that we do not reject the null, that means we accept the null. Whatever the null is saying is actually true. So you're basically here going to say, which indicates that there is probably no relationship between gender and the preferred brand of cold drink. All right, so this is it for question 9.1. So that's quite straightforward. It naturally is a bit more work because you do have to calculate the values of FE and then that last column for your chi-squared statistic. However, it is quite a straightforward question. It's often easier than the hypothesis testing because you don't have to worry about identifying what type of test it is and so on. You know that it's a you know that it cannot be a two-tailed test or a one-sided lower tailed. It can only be a one-sided upper tail test. So it does end up being a little bit easier, but again, obviously the option is yours, whichever you prefer and are more comfortable with. So I'm going to erase what's on the screen because I need a bit of space for the last question. So the last question now is just another question based on your hypothesis testing. And it says to you that the marketing manager of a company that manufactures bubble bath wishes to know whether there is a preference amongst the three different bubble bath fragrances that the company uses. A random sample of 900 customers were asked to indicate which is their favorite fragrance, and the results were as follows. So here they've given you the fragrances. The options are berry, coconut, and lavender. There are 300, sorry, there are 900 in total. And then it says use a 1% significance level to test whether there is a preference amongst the fragrances. So here exactly the same steps are followed. Start off with your null and alternate hypotheses being written out in words. So the null hypothesis will say, remember they're looking at whether there is a preference amongst the fragrances. So your null will now say that there is no preference amongst the fragrances. And your alternate will say the opposite, that there is a preference amongst the fragrances. And that is your null and alternate hypotheses done. The second step is to draw up your bell-shaped curve. It is only a one-sided upper tail test, only ever a one-sided upper tail test. Your region of acceptance is your critical limits and everything below it. Your region of rejection is everything greater than that critical limit. So how do we get to the critical limit? You need A, which is your level of significance, which is 1% as a decimal. That's 0.01. Your degree of freedom, when it is not two-way table, remember in the previous question, this was a two-way table. That's what it looks like. We said the degree of freedom is calculated as R minus 1 multiplied by C minus 1. But when you don't have a critical table and instead you just have a normal table, or maybe they just wrote it out in words or in a sentence or a paragraph, if it's anything other than a two-way contingency table, then you simply calculate the degrees of freedom as n minus 1. And N refers to how many categories there are. So there are three categories here of the bubble bath fragrances. So it's going to be 3 minus 1. So this is 2. And now we're going to go to, remember your critical table, your table 3 of your appendix. A is red going across, so that's 0.01, and the degree of freedom is red going down the first column, so that is 2, in line with 2, and 0.01. You have a critical value of 9.210. So this now is the value that will go into your diagram. So I'm just going to take that out. And this would be 9.210, but you just need to write out the rejection region in words. So you will say reject the null hypothesis if the chi-squared statistic that we'll be calculating is greater than 9.210. All right, so that's done for step 2. Now for step 3, which is your region of, sorry, not your region, your calculation of your chi-squared statistic. So now you have your options or your categories. So your categories are berry, coconut, and lavender. The FO values are always the ones that are given to you in the table. So that's 320, 275, and 305. Then they said to you, and this is now for your FE, they said to you that they had sampled or asked 900 customers what their preferences were. Now here, all you're going to do is for the FE value, split the 900 equally amongst the 3 options of the fragrances. So 900 divided by 3 would tell you that FE, remember, you're taking the 900 and splitting it over the total number of categories or options, and that would tell you that FE is equal to 300. You don't need to show that working out. I'm just showing it to you so you know how we calculated it. And then in the last column, it's FO minus FE squared over FE. So for the first one, remember, it's 320 minus 300 squared over 300. So this would be 1.33, 2 decimal places always. Then the next one would be 275 minus 300 squared over 300, and that's 2.08. And the last one is 305 minus 300 squared over 300. So this would be 0.08. And now we can calculate the chi-squared statistic. If you add up that last column, it gives you 3.49. Then we simply look at where does this 3.49 fall on the diagram. And again, it's literally just treating it as a normal number line. So this would be somewhere here, which is your region of acceptance. So now you're going to say, therefore, do not reject the null hypothesis which indicates that, and again, go back to your null and alternate hypotheses. If you're saying that you do not reject the null, that means you're accepting the null, and then whatever the null says is true. So it indicates that there is no preference amongst the fragrances. And that is it. All right, so that is it for the NSS session for the exam paper from 2024. I hope that this has been extremely useful for you and you will be able to clearly identify which are the questions you're more comfortable with and also anything that you were struggling with. Hopefully, this session has been useful. It helps you to feel more positive about a particular question or section. I also just wanted to show you the tables that I was referring to earlier. So here's table 1 on the left hand side. This is your normal distribution table, your Z values. Then table 2 were your T values. We use this for learning unit 8. So this was actually, and I'm just going to write that down here. This was for learning unit. I'm going to write it on the top. Learning units 6 and 7. Well, mainly the last part of 6 that leads to 7. Then this was for learning unit 8, your hypothesis testing. And then this was for learning unit 9, your chi-square distribution. And remember, I drew up for you when we were working with learning unit 8, the hypothesis testing. I said to you that there is a table that's not in the statistical tables at the end of the textbook, but rather it is in the chapter itself or in your slide. Your lecturer has possibly included it. And this is something that you will have to learn. If you choose learning unit 8, which is question 8 in your exam, as the option rather than learning unit 9, then you have to learn this table. So I'm going to write this here just so that you know if you are choosing learning unit 8 as one of your options, then you do need to learn the values on this table. Remember, we use this one. We use the two-sided, sorry about that. We use the first one, which was a two-sided test and a 1% significance level. And remember, we said it was 2.58. So a positive 2.58 on the right-hand side and a negative 2.58 on the left-hand side. So these are all of the tables that you will need. Table 1, 2, and 3 are the statistical tables that will be included in your formula sheet or at the end of your paper. But the table on the right-hand side here, you will need to learn if learning unit 8 is an option. All right, so that's it from me, from my side. Thank you, everyone. It has been a great semester. I'm sure that you all will do wonderfully well in your exam. Good luck for all of your exams, including statistics. Make us proud and all the best for the rest of your degree. Cheers, everyone.